background is actually in civil engineering, and let me share my screen. And what I don't want to do is, all right, can you see my screen? And is it a full
Yep.
screen? Okay. So I'd like to have a conversation, and I apologize for having to do this remotely. I am in Sweden on a Fulbright. But I would love to have a conversation about some of the AI and civil infrastructure and some of the challenges that we face in this field. Everyone in this meeting, right, is going to know more about AI than I will. So I don't want to do the classic academic thing where I come in and talk through some, algorithms. I'd rather show you some of the challenges that we've been tackling in a very broad range and kind of hopefully open up your eyes to maybe some of the interesting challenges that can be affected by AI in civil infrastructure, and also the human side of this, right? So humans interact with civil infrastructure more than anything else. And the only thing that probably leaves a bigger impact on your memory is the health care or health system. So civil infrastructure is super important. I want to talk a little bit about the lab in general, just because it's going to help set the context of some of the slides that follow. So we use foundational science, right? We're very interested in the foundational science to develop essential tools. We really want to make things that people who follow us can use. And from a computer science perspective, this is not new to you, right? Open sourcing tools is very common in your domain. It's not so common in other domains, to the point where I'm trying to make it more common. But we want to develop tools for those that come after us to solve real world problems, right? We're not interested in doing kind of science for science's sake. We want to leave the planet a better place than when we showed up. We are engineers, is what I like to say, mostly. The group is made up of a lot of engineers, some computer scientists, a good chunk of computer science, computer engineers, a few physics, math, some other interesting majors. So this is the group in general, or was the group about a year ago. We work a lot on sensing for structural health monitoring, additive manufacturing, environmental health quality. We do a lot of data assimilation. So we use structural data that's trying to mix data and models, batteries and additive manufacturing, a lot of AI ML. So we're very interested in explainability, very interested in automated decision making, and then a lot of time series forecasting. And then the last one that might be of interest to the group here is we're very interested in embedded systems, right? So a lot of microcontroller-based embedded systems, a lot of real-time operating systems, and FPGAs. So all of this is done with great collaborators all over the college, including quite a few in the Department of Computer Science and Engineering. I apologize right off the bat if this seems a little simple, but I want to expose everyone to what civil infrastructure is. So to me, I walk around any city I'm in and I try to take pictures and look at the infrastructure, but I understand that may not be everyone, right? So civil infrastructure includes the essential public systems and is roads and highways. So roads and highways are very interesting because you have structures like bridges, and then you have materials like the road you drive on. Bridges and tunnels, water and sewage system, that's something that you should be thinking a lot about. These are very old systems that are in great need of retrofitting and are very expensive to retrofit and very hard to do. Dams, levees, and flood control structures, very relevant to just what happened in South Carolina. Levees are a very challenging topic, right? You try to build huge dams to hold back the water using locally available material. It can be quite challenging. And then something we won't talk too much about, electrical grids, transportation networks, and more. The electrical side of infrastructure is a whole different animal that we won't really discuss. So infrastructure and maintenance upgrades, these are very important things, right? So on the top right is a picture from Germany, but this can happen anywhere, right? Whenever you're having to upgrade infrastructure, it's incredibly expensive and incredibly detrimental to people's lives, right? So this isn't like upgrading a software package for an online shopping thing where maybe things show up a day late, right? If someone's in a wheelchair, they can't get across this trench. If they're not able-bodied and willing to jump, they can't get across this trench. And so it can add a lot of hassle to people's life. And that's one of the reasons that we don't maintain infrastructure as much as we should, is because it adds hassle, which then comes back later and bites us. The I-35 bridge collapse is on the bottom right. This was in Minneapolis. This was a bridge, lots of issues, lots of human factors here, but a plate cracked and wasn't appropriately corrected, and the bridge catastrophically collapsed, killing multiple people. And so, but these are very expensive, right? The bridge collapse that happened in Tennessee, very expensive. The bridge collapse, slightly different, that happened in Baltimore, very expensive, and eat up a lot of the budget and maintenance, right? So these are critical for public safety and economic stability, right? Necessary to handle our increasing demand and urbanization. The world is urbanizing. The United States continues to urbanize. The state of South Carolina continues to urbanize. In the last census, the state of South Carolina gained population, but over 60 or 70% of the counties in the state actually lost population because people within the state are moving to the big cities and people from outside of the state are moving to the big cities. This is not something that happens in the South as much, but where I'm from, up in the Midwest, you have a lot of rust. So top right is water quality. This is kind of what happened in Flint, right? So our infrastructure affects the water we drink, the water we bathe in. One option is you just buy all bottled water, and that's a completely different conversation we can have about the effects on the environment of buying all bottled water. The bottom right is the Arlington Memorial Bridge, right? And so this is outside of Washington, D.C., and we put salt on bridges to keep ice off of bridges, and this is what happens. And so how do we how do we maintain this infrastructure that's often built in an unsustainable fashion? I'll try not to go off on a tangent, but as we continue to build suburbs, typically are built by private companies that put a road in, and then they put a bunch of houses around the road, and then they gift the road to the city. Often the tax income that comes from the houses around the road are not enough to pay for the road. So who pays for that road replacement resurfacing in 20 years? There's a huge kind of movement called strong towns, and I would encourage you to look at it. Just because the government may show up with a check once to pay for infrastructure doesn't mean that the localities actually have enough tax base to maintain the infrastructure going forward. I also want to look at the role of AI in civil infrastructure. What we want to move towards is condition-based maintenance, right? And that's in the top right of this plot, which is several years old now, but it was from my dissertation, so maybe I'm just emotionally attached to it, right? On the bottom left of this arrow system, we have reactive maintenance. It's very cheap, but the benefits are quite low, right? I get a pothole, I run out with a shovel, I fill the pothole, right? Okay, well, that's fine, but maybe I should plan my maintenance where once a week I do all the pothole filling, or once a month. Maybe I do preventative maintenance where I put more sealers on my potholes. Or maybe I can do condition-based maintenance where I just say, this road does not need to be repaired because, it's just not worth the effort, right? And so these are kind of the roles of automated decision-making, data analysis, machine learning, and I'm using the terms AI here to encompass all of that, kind of a very traditional aspect of AI, not just the newer, larger language models. I also want to talk about the intersection of civil engineering and AI, right? Or these automated systems. All right, you're all, everyone here is very smart, right? Otherwise you wouldn't be in a graduate program. And you have a lot of computer skills and, like technical skills, data processing skills. How do you actuate the world around you? How do you take those inputs and make them create changes in the world around you? It's not easy, right? Infrastructure is not something where you can actuate at a low cost. So on the picture of the right here is Örebro, which has this fancy castle. It's kind of in the middle of Sweden. I was on a tour and I went down the sidewalk that said no access. and people said, you can't go down there. And I said, don't worry, I'm a professor taking picture of infrastructure. It gets you out of a lot of things. And so I took the picture of this floodgate, which I absolutely love, right? Because this is a real world way that we can influence the water around us. So they're very interested in keeping the water high because it makes the water around the castle and the city look very pretty, right? And I knew instantly when I showed up in this area that the water was artificially high, and I didn't know why, because I asked if the city flooded, and the locals said no, the river never floods, but the river was too high and having not rained recently for it not to flood. And then I found this gate, which keeps the water artificially high just to make the downtown area look pretty. But it gives us an idea of these are things that we can automate, right? So if I build a weather forecasting system that knows it's going to rain tomorrow, I need to open up the dam today to keep the water low. I can't be completely reactionary. All right, and so we want to move kind of toward an automation and civil infrastructure leveraging IoT. Really want to move to this idea of smart cities. We don't want a city to be smart so the city has a high self-value, right? That's not what we're talking about. We want these AI-driven infrastructures to enable the key, is key in enabling these smart cities for the people that live in the cities. So something to think about of how do we actually actuate and make the city life better. So that's kind of a background on civil infrastructure, very broad, I understand. We'll talk through some applications and case studies, and feel free to speak up. I can't see, but if you have a question, just ask it. I'd love to have a conversation about some of the technologies we're developing. So one of the things that we've been working on a long time is structural health monitoring, right? We want to enable real-time modeling, monitoring, and early detection for predictive maintenance. This enables us to improve safety and reduce costs. We cannot afford to replace even a fraction of the bridges in the country. So we have to be very careful about what bridges we do replace. And so AI forms a huge part of this. If you type in structural health monitoring, over half the papers will be related to AI and ML and how do you process the data. It is a very interesting data set because there's not a lot of data, right? The data that you get from a bridge is very expensive, typically time series acceleration, and very hard to get seasonal variations in the data. So it's really a small data challenge, which is kind of a growing field of AI, one-shot learning. So we've been working on this for a long time using these large area capacitive sensors that we've deployed on a bridge now over 10 years. On the bottom right-hand side, you'll see a bridge in Missouri, and there's a fatigue crack, and these sensors monitor the fatigue crack, and they stretch over the crack. So we've developed AI algorithms, right, to kind of process the noisy data to provide a crack growth indicator that's at CGI, where we can monitor the crack growth using a very statistical analysis approach. And that's because you have a lot of changes in humidity, you have a lot of changes in temperature, you have expansion of the joints in the summer, contraction in the winter. So it's not just look at the data spikes, right? There's a lot of data we need to pull out, and that's where a lot of the machine learning applications are coming from. I also want to take a chance to express at this step here, we do need a lot of help in developing better AI systems for infrastructure. Civil infrastructure is and civil engineering is very different than a lot of the traditional engineering fields that you might study in college, because 99% of civil engineers, the people who graduate with a civil engineering degree, have a PE, or they are a professional engineer. And so you have to have a PE sign off on things that kind of certifies that they're safe for public use. And that's very different than a lot of other places where you can, the terminology might be move fast and break things. And in civil engineering, it's a very regulated field because it's in the public interest. And so as you're developing algorithms for these things, you kind of have to find a professional engineer to work with if you want to actually get these deployed onto real world systems. Something else that might be quite interesting is we have been developing LSTM based compensators and more recently transformer based compensators for embedded systems, and that's actually these little sensor packages on the right. And then we have these drones that will fly up and deploy the sensor packages to the bottom side of steel structures, and we are measuring the acceleration signal. Now, the accelerometers are not perfectly accurate, so we use kind of embedded AI, these LSTM compensators, to filter out the noise and pass a state at the lower levels of the frequency domain to help clean up the signal, right? So we're very interested in autonomous sensor deployment, edge AI computing, and these efficient resource use, right? How can we do the computation at the edge so we only send back the information that we need? Lots of other applications for things like this. We're definitely leveraging a lot of the work that's been done in edge AI for biomedical applications, where patient data is important. For us, there's not a huge security risk of sending back data from a bridge, but we don't want to pay to transport more data over the airways than we have to. And this is a lot of these are in rural locations, on the bottom side of bridges. You don't actually have very good like cell network coverage, right? You might have decent cell coverage if you move a foot to the right, but when you're magnetically attached to a steel beam, you can attenuate a lot of cell signal. Another challenge that's really interesting and in terms of an AI methodology is water quality monitoring, right? So there's been a lot of work on real-time monitoring. You can buy sensors for things like pH, turbidity, contaminants, but lots of emerging contaminants, PFAS, hard metals, heavy metals, sorry, PFAS, so like these forever chemicals. There's a very big interest in early detection of contaminants, right? So you think about all the flooding that just happened. When that hurricane goes through North Carolina, there's a lot of pig farms in North Carolina. What happens to the runoff, right? Is that water safe to be in? What happens to the ecosystem of that water? Does that get down to the estuaries and affect clam life? So lots of kind of things that we're looking at. Of course, some of the AI ML applications here are kind of predictive analysis, automated alerts, things of that nature. So one of the things we've been developing is a nuclear magnetic resonance-based water quality monitoring with online learning. And this is a really interesting project. Been working on it very hard over the summer. And I don't know if you know what NMR is, but maybe you know what MRI is in a hospital. And so MRI is magnetic resonance imaging, and that makes a picture. NMR is a technology, nuclear magnetic resonance, that makes a pixel of that picture. And you just measure the precession of a hydrogen atom and how it decays. But your water never just has one contaminant in it, right? In a lab, we like to take distilled water, put copper sulfate on it, and now I can detect copper. What kind of machine learning methodologies can I use to extract multiple contaminants from a single sample? And so we've had some good luck doing that for jet fuels. We've had some good luck doing that for copper and wildfire ash. But these are the kind of things that we love to get help from those in kind of the computer science field and have had help in the past. So we've done AI-based relaxation analysis and adaptive learning. So that's an idea that we can put this system next to a lake or a river, and we can continuously sample. And maybe when we get a lot of uncertainty in our classification-based method, we take one sample back to the lab, run a battery of tests on it, update our prior, and then continue to sample. We've also been developing these drone deployable in situ water quality monitoring sensors. Again, we're very interested in kind of edge computing and what kind of algorithms can we run at the edge. Maybe particularly with this project, we're looking at federated learning, not so much from a cybersecurity aspect, right? But from distributing these machine learning algorithms across a variety of hardware systems. And so we drop these packages from a drone to do real-time monitoring. It's pretty trivial in terms of sensing. So pH, total dissolved solids, temperature, turbidity. But one of the things we're wanting to move towards is like, can we help to forecast algae blooms, right? And these are not kind of purely data-driven approaches. We still have to understand the physics, but definitely a need for those who have more of an expertise in some of the data-driven application systems that kind of come from a computer science background. I'm a bit of a train nerd, so I apologize. There's going to be a couple train pictures from here on out. The bottom train is the X2000, which is Sweden's high-speed train. And it's quite fascinating because Sweden has about the same population density as America. And this was the train that kind of proved that you can have trains in a sparsely populated area. So maybe there is hope in America. We'll see. There's been lots of work in traffic and transportation. Roads are very expensive. There's not a lot of actuation you can do on this, right? So on the top, you'll see kind of a dynamic lane system. These work great until somebody is tired and runs the wrong way, right? So sometimes you need more gates or things of that nature. But that's one way you can actuate it. Another way is kind of optimal train, scheduling and routing. Maybe it would be nice, say, to have 5 or 6 trains a day from Stockholm to Gothenburg, but maybe you only have 3 trains a day, and the other spots at your train station are taken up by running them to smaller towns, right? Because it's not always about how many people want to move from A to B. It's about what kind of induced demand can you create. And when you're a state-run train operator like SJ is, they have a public good that they're trying to serve. So lots of operations in that. Lots of environmental benefits. One thing I won't talk about is the electric scooters that proliferate downtowns now. That has come from a computer science background, which is something that several city planners have mixed feelings about the electric scooter conundrum that is happening in urban environments. So something to think about. Another thing that we've been looking at a lot more recently is electric aircraft optimization. Aircraft optimization is a huge field, right? Lots of very smart people have been working on this for a very long time. And aircraft optimization is about one thing. It's keeping your plane in the air as much as possible, right? When you start to look at battery electric aircraft or hybrid electric aircraft, if you want to look at probably the farthest along electric aircraft company is Heart Aviation. And actually from my window, I can see their headquarters across the bay here in Gothenburg. And you can look that up, and it's how do you manage these battery packs from as you pick routings, right? So if anyone has an electric car, you'll know that you're not supposed to charge it up to 100% every day, right? Your battery will last quite a long time if you go from 60% to 40%, but you just won't be able to drive very far. And that's very different than pumping jet fuel into an engine. So we've been doing a lot of kind of load sharing analysis for battery life, a lot of predictive maintenance, battery degradation prediction, using a number of models, but mainly kind of physics-based models, and optimization techniques, which are, I love, there's been a recent discussion on using model predictive control in large language models, which I don't pretend to be an expert on how that works, but having done a lot of work on model predictive control, it just makes my heart happy to see some of these physics-based tools we have from control theory making their way back into hopefully making like large language models more believable. So these are pictures of the flood in Colombia from 2015 or 2016. Either way, so these are Colombia floods. And another application we want to talk about is flood modeling and forecasting, right? This is an incredibly dynamic situation. You'd think, well, I just train a data-driven model on the flood. I know how Colombia flooded in 2015, so I should know how it's going to flood in 2024, right? The truth is that's not at all how that works. You don't know, some of Rock Hill's, like what kind of development has happened in Rock Hill, right? And so that water comes in here at a different rate. Rain does not spatially fall evenly, right? You can have quite hot spots of rain even in a storm, and how that falls and what it falls onto is very important, right? Because one of the things you want to do in civil infrastructure is like create pervious concrete, and it holds water for maybe 24 to 48 hours and slowly lets it out onto the creek. But as we continue to pave everything, all the water that hits the pavement instantly runs into the river, instantly runs into the creek, which runs into the river, which creates a flood. So flooding's not too much water, right? It's too much water in one place at one time. If we can find a way to separate this water out, we can help to manage floods, and AI can help do a lot of that. But it's not just it repeats and it repeats. As we continue to change the environment around us, we continue to change how these floods happen. And so if you've ever been trying to go home and you live on the south side of Columbia on a day that flooded, you'll know that the Rocky Branch, which runs kind of behind 300 Main and Swearingen, will often flood at the bottom of the creek. And that's a very flash flood environment. That entire basin, right, is urban. So the water that hits it runs off very quickly. If you've ever been up to 5 Points to the Martin Luther King Park, it's a really nice park. It used to have houses in it that were torn down, and then it has what kind of looks like a marshland. And the whole idea of that park is just to hold water for a couple of hours, so it doesn't all rush down behind 300 Main. And so we've been developing these drone deployable water height sensors in collaboration with the DNR. I'm sorry, not DHEC, which is now the South Carolina Department of Environmental Services. And these dam water height monitors, that's what's on the bottom right. I've been developing apps to help track all of this. And then in collaboration with our civil engineering colleagues, have been developing uncertainty models and Bayesian optimization techniques to help take all of this data and feed it into the flood modeling technique, right? What you'll notice here is that our group in particular is very interested in how do you develop sensing systems that can capture data of importance, right? Everyone would like to be able to use the easiest data available, and sometimes in like a civil engineering context, that becomes, used to be Twitter or X or social media data, or maybe live feeds from cameras, but that data isn't always where you want it, when you want it, and can easily saturate your system. So a lot of work has been developing on kind of getting higher quality data. Another challenge that we've been working a lot on with edge computing systems have been geotechnical monitoring. Levees are fascinating. One, they protect billions of dollars of built up human environment, right? So houses, farms, factories, everything. When you build a levee, right, you don't keep the river in the banks. You keep the river in the banks where you are, and it's kind of like declaring war, right? The community downstream now has to build a levee, and the water will either go until it hits the ocean, or it busts a levee. Those are basically your two options. And so levees at the same time are built with whatever material is local, right? You don't get a choice of high quality dirt and clay and substrates. You get what you have, and then they're incredibly unmonitored. If you ask and I don't want to throw anyone under the bus here, but if you ask the South Carolina Department of Dam Safety or anyone, how many levees are in the state, they'll just kind of look at you and smile, right? Because we don't even know how many miles of levees are in the state of South Carolina, or who owns or who is required to maintain all of the levees. So lots of good work has been done kind of from an AI/ML perspective on satellite-based imagery of monitoring levees. Like you might have more grass growing in one part of the levee, which could show you have an excessive amount of moisture, right? So you can think of there's a company and all they do is take pictures of dams and levees. And when it has a lot of moisture, they go and they sell the picture to the owner of the levee and try to get them to repair it. Although some of these levees, like we don't even know who owns them, or if it even is a levee or it's just a natural berm. So lots of interesting kind of predictive maintenance challenges with levees. So we've been developing UAV deployable kind of soil saturation sensors. Here's kind of some very basic classification on the bottom right, but essentially they're edge computing devices that we can drop into a levee. And then at the end of the spike, we measure the conductivity of different points on the levee, and then we can map full field saturation plots on the right. Soil is incredibly fascinating. I'm not a geotechnical engineer. I don't pretend to be a geotechnical engineer. But the thought experiment I would encourage you to think about is if you've ever seen anyone try to pour water on dry soil, right? What happens in comparison to like if you try to pour water on like soil that has some moisture in it? You know, to me, well, you know, you might logically think that dry soil would soak up water faster, but it doesn't, right? Water will actually run off of dry soil. And so partially saturated soil is what will soak water up, which is why you get flash floods in the desert, right? Just because the water falls on the desert doesn't mean the desert can take it. It's too dry. And so these are some of the challenges that we have with levees. Soil is an incredibly challenging thing to model and really has a lot of benefits for data-driven modeling. Has a lot of benefits for data-driven modeling because it's such a complicated thing to model. And it's changing with the climate. There's some really great work out there, including by my collaborators at Jackson State, looking at how changes in climate have changed patterns in rainfall and what that means for all of our infrastructure all over the country. We've also looked a lot at LiDAR-based monitoring. And so, you know, LiDAR is kind of like light-based radar for a very non-technical term. You know, you shoot a light at a structure, the light bounces back, and you can kind of measure the topology of the structure. And so on Jackson's, in the state of Mississippi, they have a lot of challenges related to expansive clays and soils, either soils that shrink and swell a lot. And again, do you want to build the highway embankment out of an expansive clay? Absolutely not, right? It's literally the worst soil in the world that you can imagine to build a highway embankment out of. But soil is expensive to move. And so you build it with the materials you have, with the data you have, which might be the rainfall for the last 50 years. But as we talked about on the prior slide, the rainfall all over the country is changing because of the way the climate is changing. So how the rain fell in 1950 is not how the rain's going to fall today, right? We get a lot more rain in the Southeast, parts of the Midwest are drier, and so our expansive clays have become more of a challenge. LiDAR has become a very fascinating tool, but it gives you millions of data points. And how do you process millions of data points? It can be quite challenging. So we've been looking at topological data analysis to do this. We've been looking at data augmentation techniques to do this. Lots of kind of large data spatial processing, which has been quite fascinating. On the bottom left, you'll see kind of, you know, foundational machine learning, I guess, you know, maybe what you learn in kindergarten or something, principal component analysis. But even this can be quite powerful when run through TDA, which is what happened here. And you can see that in certain parts like June, the PCAs are very, very different than when you have kind of your fall winter season. So in the summer, the soil expands, and in the winter, it contracts, and it's slowly cracking the road, and lots of lawsuits and post-geotechnical work and challenges that happen from there. Here's a cool picture I took on the way to work the other day of this Volvo data collection video car. There's an autonomous boat that sometimes runs by my apartment. And I was talking to a professor who works on it. And they're pulling in about 2 gigabytes of data every minute, right? And so just a tremendous amount of data that they have to then process on a 1-hour cruise to try to make an autonomous docking boat. So one of our issues with civil engineering is kind of data quality and availability. I can get you a lot of data. Does that data have value, right? We have limited access to high quality labeled training data. And the labeled is particularly important here because we may not even know how to label it, right? So if you look at some of the geotechnical problems, I can get you data of a geotechnical persuasion. I don't know if that levee is good, right? And I might not know if that levee is good until the next flood, but then it's too late to do anything about it. Or you take core samples, but people are very nervous about taking core samples because it's destructive, things of that nature. So model interpretability, we want to be able to trust the decisions, right? These aren't like, you might like this video. Oh, you don't like that video. What a bummer. Well, maybe you'll like this show, right? We need some real decision making that's explainable here. Integration with legacy systems. This is super important. You might have a great idea, but does it work with the systems we have? And I cannot express how old some systems are. For example, this is just a crazy statement. The pumps that run, the water pumps that keep water out of New Orleans are 27 hertz, 3-phase motors. They were wound by Thomas Edison, not Thomas Edison's company. They were wound by Thomas Edison. That is how old they are, right? So one, it's very impressive that a motor can last 100 years until you try to integrate that with a modern system, right? All of a sudden you will find, real hardware that's been running at the back for a long time. Scalability is a huge issue, right? So ensuring that models can scale across diverse infrastructure networks, both in the city and outside of the city. These are not run by private companies that get to decide this part of town gets a scooter and this part of town doesn't, and we're going to geofence the scooters out of the poor part of town, right? Because they keep getting thrown in the creek. Civil infrastructure has to kind of serve all of the community, and so the challenges are very different. There's regulatory and ethical concerns, right? So navigating the regulations, privacy concerns, and the issues surrounding AI deployment in public systems. So it's a much harder field to crack. Some of the opportunities for computer scientists, I'm getting very used to. Sweden doesn't have cool blue and green bike lanes and walking lanes, but Sweden has all sorts of bike lanes and walking lanes that are separated. And I'm getting very used to kind of working with these and kind of thinking about all the ways that the design went into these, right? These aren't just laid down on a street haphazardly. And you can see, unlike America, and America's getting better. I mean, Colombia is getting better in the 6 years I've lived there. Our infrastructure is becoming more, the infrastructure has greater access for people of different physical abilities. But it's still kind of like, here's a road, and then we put down a bike lane. And in Sweden, it's a very different application. So big data analytics can really help to drive how do you do some of those designs. The automation and optimization, right? How do you plan the trains? If you have congestion pricing, how do you maybe tax cars different amounts at different times to keep them out of the city when you're running more trains? And then, of course, IoT integration, right? So that's something that I'm super passionate about. Kind of design of systems that can connect infrastructure to the internet of, the classic Internet of Things for seamless data collection and communication. I want to leave with this picture, which I will try my hardest not to let my blood boil. This is the Ames City Council meeting. And at the top, you will see changes to zoning. And this might get some of you upset based on the fact that there was, quote, too many college kids living in these particular areas. So I went to a few city council meetings. I owned a house. I had bought a house when I was a teenager, 19. I wasn't going to college. I never planned to go to college. And it was insane to me that the city was trying to keep age groups of people out of different parts of town. And I don't know what happened, but I will want you to look at the bottom right picture of this. And I would ask you to think about who's in this picture, right? So this is a Thursday night at a city council, and it'll be the same if you go to Columbia. You see a lot of suits. how many people wear a suit on a normal day, right? So what you won't see in this picture are any young people who are being affected. What you won't see in this picture are mothers of small children or parents of small children who have kids to take care of on a Thursday night, right? What you see in this picture are property developers and heads of their local housing communities, right, who are there to protect their interests. And that's who the city council listens to. So as we think about these challenges of civil infrastructure, right, we have to collaborate for success, right? Well, there's a couple things. One, as a computer scientist, right, you need to collaborate for success. We have to work with civil engineers. That's essential for solving the infrastructure challenges. This is not just something that gets a layer of AI plastered over it and everything's good. We have to have co-generated knowledge, right? And so that's engaging with communities to create solutions that are inclusive and culturally sensitive. And I say that not to throw out a pointless buzzword, but if it's not serving the people who live in your community, then what's the point of the infrastructure investment? We have to design for all, kind of diverse social needs, age, physical abilities, culture, kind of when developing these AI solutions. This isn't, so one way to think about this is like the languages that we use on apps, although that is getting a lot better with automatic translation. Another thing I like to think about is the old DC fast charging standard in the US before they switched to the Tesla standard. I don't know if any of you are maybe 4'10" and 90 pounds, but if you take someone who's not very big and have them try to plug in a DC fast charger, it's funny in the sense that, like, if you're just doing it as a demo, it's funny. It's not funny if you're stranded on the side of the road and you need to charge your car and you are not physically large enough to plug in this charger that was designed by a committee of bureaucrats, right? And so that's kind of what we talk about design for all. And shaping the future, you know, the potential here for kind of these automated systems and infrastructure really depends on interdisciplinary teams and the ethical design, right? And again, this picture on the right just still irks me. I was the only college-age person who showed up. And what was incredible was, of course, what I was advocating for against passed, right? I think there was 9 people, 7 voted 2, but of the 2 that voted against, on the city council meeting, they both came up to me after the meeting and said they were so happy that I was there to actually make a statement for the other side. So there are people in government that want to listen to you, but if you look at this picture, you'll see the normal type of people that show up to influence the government. So something to think about. Ames is still a great town, still great people. Just this one thing really, really frustrated me. So we'll close with this cool picture of the X2000. I tried to get a picture, but I couldn't get a picture that beat that. And so with that, I'd love to open it up to any questions or comments, and understand that this is a very different talk than I would give if I was like talking to, oh, I can stop sharing. If I'm talking to civil engineers about AI, right, I'd probably talk more about the machine learning aspects, but I'm very interested in expressing some of the challenges we have in trying to make infrastructure better and trying to solicit some help from very smart people. So.
Great. For me, this is exactly what I was hoping that our students will hear. I guess I hope you got to get a sense that there are real and significant AI challenges, or even computer science basically broadly challenges, as you start looking at the area. Just before this particular seminar started, we had a bunch of associate professors in this space next to here. And I discussed at the AI Institute, we have collaboration with a lot of different fields. smart manufacturing, social good and social bad, science is of different kind, particularly neuroscience and cognitive science, a lot of health related work that we do. And I think, you know, on the campus, Austin has built among the best, interdisciplinary program, particularly civil engineering and computer science. And hence I wanted to look at that. Also, I mean, as the system, as our field becomes more applied, we really have to understand the domains. So many times, many of my past students have had career success because they not only knew right science, but they learned how to understand the requirements of a particular application domain, particular customer, and so on and so forth. So I hope you learn to pay attention to these kind of opportunities and such. Does anybody want to ask any technical question? Yeah.
I would like to hear more about how they use AI to reduce traffic.
Okay.
Road congestion.
Okay, Austin, the question is your effort or work on AI to use to reduce traffic or congestion.
So that's a very good question. And I would say in America, we don't. So the challenge is actuation, right? What levers do you have to pull on people? Because in America, we refuse to say you can't drive your car, right? So in London, one thing they'll do is they can have dynamic pricing. Well, parts of the UK, they'll have dynamic pricing to try to say if there's too many people, right, we're gonna increase the price in this area. We tried to do that in New York City, and it was voted up and then shot down, and then recently it was voted up again and then shot down. And it's insane to me sometimes because when I don't know if anyone's ever been to Times Square, right? It's a culturally important place in America. People walk around. That was supposed to be temporary. It was supposed to be 1 week of a car-free Times Square, right? And then it just stayed because people loved it. I will say that one of the more convenient things I've seen is I shouldn't be so negative on traffic mitigation. If you go to Atlanta, they will meter you in some big cities, right? They'll meter you into the interstate system. So you'll have like an on-ramp with a stoplight, and those are not just randomly timed. Those are trying to meter people in to keep people feeding. But there's not a lot of actuation that you can use to reduce congestion other than trying to keep too many people from one area. But and that's the challenge, right? We can have ideas, but how do you force people to follow those ideas? So interesting. I'm sorry, I don't have a great answer.
I'll give you an example of some work that we have done. One of my PhD student, we got data from the road network. So there are sensors on the road. This was from Bay Area, California Bay Area. And so really billions of data points are collected over an entire year. So there are road links. For every road link, there are sensors. Sensors capture the number of cars passing by and the speed information. That massive amount of is captured, and we wanted to understand the impact of variety of why is the traffic slow. So first we have to understand what is the slowness of whether traffic is fast or slow is with respect to the normal times, meaning every day of the workday, the traffic may be slow during the morning rush hour, the evening rush hour. So when we want to say slow, it is with respect to the normal traffic that is at that time. So we had to collect massive amount of data and then look at the weekdays and working days and then holidays and weekends. And we by hour, so you have 24 hours day, 7 hours, 7 days a week. For every hour in a week, we computed the normal traffic. And then we said, then because of that, and that's a massive computation. I have a paper I can share with you, discuss in great detail. My PhD students, certain topic, a video is there also. You can, listen to that and understand what he did. And then when we get an exception, meaning that sometimes time when the traffic is slower than what it should be for that time of the day, then we would try to the application was built for the purpose of finding out why that is so. So we had variety of sources of data. One source of data was tweets. You have to geolocate the tweet, which is why some tweets will have the geolocation, others won't. So that itself is a very important and difficult challenge when you might have a tweet, but it does not say location, or it says the name of a landmark, but there is no geocoordination. So you have to convert that into geocoordination, right? So that is the work you have to do. It would have information from the transportation agency's website, because there is a let's say planned road work. So that it could be slow because of that. It would have information. We had information about a variety of events planned. For example, you have a big stadium, and if there is an event at a stadium, obviously things would be very different in terms of traffic. And so there are multiple sources of information, and we had to associate when we find slowness, what is the likely reason for the slowness, and then based on the reason predict the likely resolution. For example, if it is because of an event, then typically after the game is done, it resolves over a particular period of time. So you would have that kind of information. But the traffic related issue is extremely challenging, and I just gave you some interesting points of those. And we had really massive computational need when you have to find the normal traffic for every hour, that kind of stuff. Very, very interesting topic. Yes.
And that one intrigues me because of it also links into the whole ethical issues. Because like, I know, for example, Washington DC does this sort of thing with the metering and changing the prices, and it's become the kind of thing where you don't take into consideration those who work but are not of high income, and they're left stranded in the slower lanes because they don't have the income to allow them to be able to pay the high rates to get into the fast lanes. And that seems to me like one of those things you were talking about the representation in governments when they make these kinds of decisions, and they're basically looking at the people who have the income already when they're making that decision. Is that something that you think that goes into those sort of decisions, or?
Yeah, man, that's a solid question. Okay, so I always like to think that no one's out to hurt the little people, right? That's what I like to hope anyways. And you got to find a way to pay for the bridge, but the challenge is like the infrastructure is so expensive. And the truth is the only way you can get people onto public transportation is to make it uncomfortable to drive. But like so I was was talking to a professor of civil engineering here the other day, and he was mentioning how gas is so cheap in Sweden. And I was like, well, why is fuel so cheap in Sweden? I thought it was expensive. He's like, well, then the current batch of politicians lowered the price of fuel because they want to be popular. And I'm like, oh, we have those politicians too. Right? So, it's a big issue. Like if people have money, then none of it affects them. And if you don't have money, you're stuck in the slow lanes. So it's that constant issue of what's your actuation, right? And what are the levers that you can actually pull to move people along? So yeah, like the dynamic pricing is great, but yeah.
As at least as some level of public transportation. So to the extent that, people, have that option of public transportation, you could argue that they have an escape valve and, that unfairness is somewhat moderated.
Except when you realize that the best public transportation doesn't make it out to the areas the lower income people live.
Yeah,
It's the inner city, the right around the beltway areas where the high expensive homes are.
yeah, no, that's true. It's not, so,
And
but,
just
Yeah.
Allow, let's say, you can pay to go to the fast lanes, or you can go if you have 4 people plus in your car.
They had that too.
They have
They
that?
had that.
Yeah,
too.
they are.
Yeah, the high occupancy vehicles, the HOVs.
yeah, but there is a lot of cultural issue also. I mean, in US, people don't want to take any inconvenience of public transportation. They want to go at the time they want to go. I mean, they don't want to, change their behavior for the time. So, I mean, that's there. In some other countries, where a public transportation is there for a while, and there are not much of an option, people manage it.
If it's faster than the car and it's cheaper.
Yeah, so, one of the largest city in India, Mumbai, has terrible traffic and extremely congested public transportation also, and highly used public transportation, the trains that they have, suburban trains they have. But people have to go early and come back late and manage the time to get by. There's no other option. So, but anyway, I think those are important issues. Social issues are, and as Austin was saying with his example of AIIMS, they are not constitutional. These guys, people who cannot afford, they don't even have time to. They can have reason to say, well, we don't have time to go to these meetings either. So they're, they will be hurt anyway because of the lack of representation too. Some of them, many of the poorer people don't vote either, or there's less voting there, right? I mean, people who are daily wages, they don't go to vote because they can't afford it, or they would other alternate things they want to do. So again, it's difficult social issue. Okay, yeah. To build what? Earthquake resistant. This may be something Austin. How can we use AI to build earthquake resistant infrastructure? I have no answer for that, but you might.
That's super fascinating. Resistant structure, I don't know. But here's something that's really cool. California has an early warning system now, right? So earthquakes are made up of like P waves and S waves, and they take time to propagate to a city. And so that's a really cool app, right? You get that app on your phone and it alerts you. You may only get 15 seconds, but 15 seconds can be enough time to hide in a corner and put your hands over your head, right? We have been working on developing GANs for better earthquake profiling. So if you remember a couple years ago, there was a super destructive earthquake in Turkey, like insanely destructive, maybe 2021, 2022. And one of the things that happened there is that earthquake was outside of the design requirements for those buildings. Now, those buildings, I'm not saying that the design requirements were, well, obviously they were wrong because a lot of people died, but they were based off of historical data. And so we've been looking at GANs, time series GANs to develop a better tools to forecast the time series signals of an earthquake and how that might propagate to a signal. But I mean, definitely the coolest thing I've seen in earthquakes beyond civil engineering, design, dampers, all of that is just the warnings that people get, right? Just so you know an earthquake is coming on your phone. So that was a very expensive undertaking by the state of California.
Okay, looks like well, there was a lot of interest, Austin. Thank you very much for talk. I think that has a lot of interest here, and I'll share with you one of our recent work, because looking at your work, recently we have had a NSF funded project with manufacturing people, McNair, and so we built a system that is deployed on the edge on the manufacturing assembly line. And so we've been developing a new generation of models we call compact custom neurosymbolic AI models. So these are small, highly targeted models, AI models for very specific purpose, demand forecasting, prediction, things of that nature. And in that sense, you might see potential, in terms of the emerging AI technology for solving some problems that, maybe somewhat different than the kind of models you used in the past, and perhaps there's something,
Yeah,
to exchange.
we have not done any neurosymbolic stuff, and I've been super interested. That and
Okay, good.
event-based cameras, those are the two things that I want to get into. So
Yeah, so we are doing a good bit of work on causal AI also, and the events are involved. And the smart manufacturing are clearly about the rare events. And we just had a paper accepted in the ACM computing surveys, which is very lengthy paper evaluating various rare event anomaly detection, basically a line of work. And I think it is. Yeah, let's see. We'll exchange that and keep in touch.
So, but it's 9:30, so I'm on my. I'm gonna close out for the day. But
Bye.
have the
Thank
rest
you.
of the day. Bye.
Bye. Yeah. Okay.